welcome back to my channel. Another new video. We're continuing the data structures algorithms bootcamp. We are continuing with the trees playlist for now. So as you know, we already did the introduction of binary trees, binary search trees. So you can check out the playlist and all the other amazing stuff that we've already done. We're doing the complete interview preparation bootcamp, notes, assignments, everything in the description below. But in this video, we're doing the second video of the trees lecture. We're talking about self-balancing binary trees. So in this video, I'm going to talk about AVL trees, and then in next videos, we'll talk about like some other types of trees like Fenwick binary index trees, segment trees, red and black trees, and then we'll do some interview questions as well for trees, which is obviously very important. You know, we did binary search, then we did binary search interview, we did linked list interview, we did recursion, then recursion interview. So for trees also, we're doing theory part and implementation part, and in the end we'll do some very important questions part, like how to identify patterns, how to solve any tree question. Okay, but in this video we're talking about self-balancing binary tree. No need to worry about if you don't know what a self-balancing binary tree is. Only prerequisite is all the videos we have done till now, and the trees video specifically that I did previously. So I'm going to start with a challenge, like what are the challenges with normal binary trees, and then we'll talk about okay, how balancing binary trees solve these challenges. And in this video we're going to look at a very popular self-balancing binary tree. Obviously we'll look other ones in the later on, but this is very important, hence I'm making a dedicated video on this. So we'll look at AVL trees. Full form, everything I'll tell you later. AVL trees. One thing I want you to notice is sometimes people get intimidated by AVL trees. Oh, it's very difficult, you know, it's very confusing. It is not confusing. Not confusing. Then what it is, Kunal? It is actually, it has a lot of moving parts. Lot of things are happening. So with AVL trees, lot of things will happen, but all of those things are very simple. Just the quantity is a little bit, it's not that high, just 4 test cases. Okay, there are only 4 cases, but still some people feel like, okay, this is too much. But I will actually teach you. So if you're looking at it for any topic, okay, not just tree, even when you do dynamic programming or when all the previous topics I've done in the past, when you take a concept and you try to memorize that concept in the terms of, oh, this concept has 4 cases, this concept has 6 cases, this concept has 10 cases, you try to memorize that without understanding what are these, why are we having these many cases, then it becomes overwhelming and difficult to you. Then you feel like it's difficult. But I will make it clear to you why we only have 4 cases, what is the significance of each case, the thought process behind it. When they created AVL, why did they only make 4 cases or whatever? Okay, let's get started. Forget about AVL right now. Let's just talk about binary trees, normal binary trees. So if I talk about a normal binary search tree, in the previous video we have already learned how normal binary trees functions. Okay, so let's say I have a 10 over here, and now I'm saying, hey Kunal, insert 5 into it. Okay, 5 is smaller than 10, 5 will go over here. I've already covered this, okay, how binary search tree functions. So if you are not understanding this, please watch tree tutorial number 1. There's a tree playlist on my channel. Now insert 15. Okay, 15 will go over here. Now insert 10. Sorry, 10 is already there. Now insert 12. So 12 is greater than 10, so right hand side, less than 15, left hand side. So on and so forth, you get the idea. So the idea is that the maximum height, let's say it's going to be log of n, which is n is the total number of nodes. So at any point of time, we have already covered in the past how the insertion and your delete and your when you delete or when you try to search an item, it will take log of n time. Very good, no problem. Okay, but the problem arises, let's say you're saying, Kunal, insert 5 in a binary search tree. Okay, no problem, I've inserted 5. Now Kunal, insert 7 into it. Okay, so 7 is greater than 5, it will go on the right hand side, no problem. Kunal, insert 9 into it. Okay, 9 is greater than 5, so it will go on the right hand side. 9 is also greater than 7, it will again go on the right hand side. Kunal, please insert 11 into it. Okay, 11 I will insert over here. Kunal, please insert 13 into it. Okay, so can you see what is happening? If I want to search 13, it will have to traverse it n number of times. So instead of log n, it is now taking n complexity, which is wrong. Whole point of binary trees is now destroyed. Whole point is destroyed. This is the problem with binary search trees. Because a chain can form like this. Even if you have something like this, still there is a chain, right? Not perfect log n is the answer. Make sense? That is the problem, and that is what we're trying to solve. So how do we define this problem? Okay, now defining the problem. Kunal, it looks like a problem when I'm looking at it from my eyes, but how do you define it in a definition? Define the problem. No problem, we can define it. So the problem is this, that for any tree that you have, let's say we have this tree, something like that, okay? Let's say we have this tree. Now here you can see that the difference of height of left subtree and right subtree for every single node is going to be either +1 or -1, like less than equal to 1, for example. So here you can see what is the height. Height is the number of edges from the node to the bottom leaf. So for every single node, let's say we're talking about this node first. For every single node, think about the definition. For every single node, the height of the left and the right tree should not have a difference of more than 1. Okay, what is the height of this tree over here? What is the height of this tree? This tree's height is 2. What is the height of this one? 1. 2 minus 1 is equal to 1. Correct. So this difference can only be less than equal to 1. So 1 or 0. And if you do set, let's say, for example, if I say for every node, height of left minus height of right can be equal to -1, +1 or 0 only. In this case it is 1, but if you have something like this, in this case this height is 1, height is 2 for this tree. 1 minus 2 minus 1, that's fine, no problem. Okay, and this you have to do for every single node. For every single node you have to do this. So now let's see, I did it for this node, right? Now I will do the same for this node. So again take this tree and this tree. Here the height is 1, here the height is 0, difference is 1 minus 0, 1. Yeah, sure, this is also balanced. Now again do for this node, 0, and so this is just 1, so I will just leave it. For this node, this is itself, it has no left or right children, so I'll leave it. And for this one, it's again just 1, as you can see over here. So pretty simple stuff. Okay, so as you can see, for every single node, I'm repeating it again and again, for every single node the left and right tree height can only be -1, +1 or 0. Let me take an example of a tree which is not balanced. This is known as balanced tree, by the way. Okay, if I write the definition down, for every node did my pen run out of ink? Not working. So Actually, this is the definition only, what formula I have just written above. For every node in the tree, the difference in height of left and right subtree of that node, for every node, should be less than equal to 1, or should be less than equal to 1. Cool. So either 1 or 0. Now let's take a look at an example, and that is a balanced tree. That is called a balanced tree. Let's take a look at a tree which is not balanced. So if I have this tree right here, okay, like this. This is okay for now. Something like this. Fine for now. Okay, let's add in one more. Okay. Now, how do we determine, Kunal, whether this is a balanced tree or not? Look at the definition. The definition says for every node in the tree, the difference of the left and right subtree height should be less than equal to 1. Okay, then I will start checking from here. What is the height of left and right? So height of this is 1, 2, 3, and height of this is 1. So 3 minus 1 is equal to 2, not balanced. Not balanced. Simple. That is basically balanced tree and unbalanced tree. I hope that is clear. Okay. In the previous example also, this is also unbalanced tree, this one. Why? Because the height of the left tree is 1, left tree is 0, right tree is 1, 2, 3. So 0 minus 3, minus 3. Not cool. Not good. Difference in height is 3 here. It's minus 3. Okay. Very simple stuff. Cool. Now, moving forward, how to solve this problem? Solution. Solution is self-balancing binary tree. For example, one of those is AVL. Self-balancing binary. Now you understand what was the problem and what problem self-balancing binary tree is trying to solve. So when you have a tree that is unbalanced, let's say you're adding something, and the tree becomes unbalanced, self-balancing binary tree will be like, okay, don't worry, you keep adding into the tree as you wish. I will restructure the tree in some way that it will always be balanced. And what is balanced? You already know the definition. That is what self-balancing binary tree is. Don't worry about how it's working. Okay, just think about what it's doing for now. We will obviously look into the entire code base, entire algorithm, all the theory, everything we'll cover in this video. So don't worry about that. Try to focus on what this problem it is solving. What is meaning by self-balancing? Self-balancing means you just keep inserting in it, and we will apply some algorithm that whenever you insert an item and that insertion makes the tree unbalanced, it will be like, okay, Kunal just added 20 in the tree, a node with value of 20, and it has made my tree unbalanced. No problem, Kunal, just add it as you want and normally, and I will restructure the tree in such a way that it will become balanced. Okay, so for example, this is balanced tree. Okay, it's the same tree as previously. So it's going to be like, okay, Kunal, right now this is balanced, no problem. Kunal is going to be like, okay, I will add one more node over here. The tree is going to be like, oh, now you added one more node. Now this tree is unbalanced. So don't worry, add your node where it's supposed to go. I will then restructure the tree and balance it. How we are going to balance it, we'll figure out later. Okay, sounds good. Let's move forward. So that is basically what self-balancing binary tree is. And one of those trees called AVL tree. So let's see how AVL trees solves this problem and what does it mean by AVL tree. So AVL tree, self-balancing binary tree, the full form is, I think based on the people who founded it, could be that. So it's called Adelson, Welsky and Landis, AVL trees. Okay, cool. How it works, let's see. Okay, so let's see how AVL tree functions. So Kunal, we know that you are saying that AVL tree is a self-balancing binary tree. Okay, no problem. Sometimes we may insert some node in a tree and that will make that tree unbalanced. We know what unbalanced means. And when tree is like, oh, Kunal, you just inserted this node, tree has become unbalanced. Now don't worry, Kunal, I'm an AVL tree, so I will make the tree balanced automatically. So obviously, if a tree has become unbalanced, then to make it balanced, you have to change the structure of the tree. You have to move some nodes around to make the structure of the tree balanced. Pretty common sense. Now the question is, how do we do that? So what is the basic method via which the tree will adjust itself? What is the basic method? Let's see. So let's say you have a node. Let's say this is a parent node. This is a child node. This is tree number 1. This is tree number 2. This is tree number 3. Okay, so there are two methods using which we are going to form our algorithm, but two basic steps. First one is, if you want to, there's only two things you can do, okay, for every node. So let's say you found a node and you're like, this node is making it unbalanced. For example, if you try to look for, you started adding it from here, let's say you started adding it from here, let me show you how it works. Okay, let me show you how it works. So before moving forward, I'll just write down the algorithm for AVL tree. Then it will make more sense. Step 1 you have to do is insert normally. Insert normally. Node n, for example. Insert normally node n. Now start from node n and find the node that makes the tree unbalanced. So you're saying, Kunal, start from the bottom up? Yes. Taking an example of the previous question, add the node normally, okay, added the node normally, start from this node n, work above. Is this node unbalanced? No, it's not. Is this node unbalanced? Yes, it is. Sorry, no, it's not. Is this node unbalanced? Yes, it is. So, is this node unbalanced? No. No, this is not unbalanced. Okay, keep moving up. No, this is not unbalanced. Okay, keep moving up. Yes, this is unbalanced. This node is unbalanced. So now we will solve this particular subtree before moving more up. That is AVL tree. For every subtree, how you can solve it is, for every subtree, think only two things you can do. Let's say we have this subtree. So in this case, in the bottom one, this will be equal to P, this will be equal to child, this will be equal to tree 1, this will be equal to tree 2, and this will be equal to T3. Make sense? So only two operations you can perform. Parent, child, T1, T2, T3. I showed you in the real world example how this is going to be related, so you can check that out. You can either rotate it on the right hand side or you can rotate it on the left hand side. if I rotate it on the right hand side, so this will go down, C will go up, C will go here, P will go down, and P will obviously go on the right hand side of C because P is greater than C, and in binary trees anything that is greater than the node goes on the right hand side. P has T3 on the right hand side, no problem. Now C has T1 on the left hand side, no problem. T2 was replaced by P. T2 is actually, I know, smaller than P because it was originally on the left hand side of P. So it will be on the left hand side of P. Similarly, this is left rotate. This is like the basic concept. Okay. Please note that the binary search tree property that all the elements on the left hand side has to be smaller, right hand side has to be bigger for every node is still holding true for this case. Originally T2 was on the left hand side of P, now also T2 is on the left hand side of P. Originally C was actually smaller than P. In the rotated one also C is smaller than P. Similarly, you can do the left rotate also. If you want to do left rotate, then okay, P will come up, C will go down, T2 will go on the right hand side, so on and so forth. Very simple. These are the two basic formulas that we will use. Okay. Very simple. So AVL tree is not difficult. It is a little confusing, it can get a little confusing because there are so many moving components. After this, we will see 4 rules of how to apply these two methods. You can apply these two methods in 4 ways. Okay. So it's not difficult at all. It's just like there are too many components. There are 2 things like this, and then there are 4 rules. And then there's the balanced, unbalanced thing. So it's not difficult at all. I hope this is clear. Very simple stuff. So let's take an example. So if I take this example over here, if I take this example, this one, like we found the tree. So you know how it basically works. That start from the node N, find the one and bottom up, and after that, using one of the 4 rules, rotate. Okay. That's it. What 4 rules? Let's see. 4 rules. Rule number 1. It's very simple. In the previous example, let's say we had a parent is over here, and let's say you have a child over here, and that child has a grandchild over here, G. Okay, and then this has tree 1 and tree 2, tree 3 and tree 4. Let's say you have a situation like this. There are only 4 rules possible. Okay, now you're like, Kunal, how did you figure out this is the grandchild and the grandchild is, let's say, not on the right hand side? That is also one of the cases that we will cover. But the grandchild is actually in the line of where the element was added. So if your element was added over here, then this will be grandchild, because it is in the line from the element added to the parent. Okay. If the element was added, somewhere over here, then this would be grandchild, because it's in the line to the parent. I hope that is clear. It's very simple stuff. Okay, let's move forward. So let's say we have one of these 4 cases. So in this case, imagine that the P point, let's say for example, these cases are for unbalanced binary trees, subtrees. So this P is where we're going to be rotating it. So in this case, what we're going to do is, if we find a case like this, we're just going to right rotate. right rotate from P. So C will come above, P will go over here, T4 will go over here, then what? T3 will go over here, G will stay here, T1, T2. Make sense? Sounds good? Okay. Case number 2. Let's say parent like this, you have child like this, and let's say here you have T4, and let's say now you inserted something, there was a tree over here, T3, and let's say you inserted an item over here. Then the item inserted in that lane, the child of child is going to be the grandchild. Okay. T3, T2, T1. These are subtrees. T1, T2, T3. Okay. All right. Now what we're going to do is, this is actually going to be first one is going to be the left case. So you have the child and grandchild, both are on the left side. Left. So left case. Here you can see that it's left right. So this is left right case. Your motivation is to convert the tree in a single line. This parent, child, grandchild, right? Convert it into a single line. That should be your motivation. So because then you will be able to rotate and make it balanced. Okay. So here you can see it was, for example, in this case, single line, parent, child, grandchild. Okay. Similarly, you can rotate. But here you can see it is not in a single line, it is zigzag. So I'm going to first make it into a single line. So to make it into a single line, I start from the bottom, and what I will do is I will put G over here. I will do left rotate C, left rotate C, that will bring G above. So it will make my tree something like this. G will come over here, and then child will come over here, tree 1, tree 2, T3. Now you can see it's in one single line. And is this not the same as this one, first one? So what is the case for first one? What do we do when we have a structure like the first one? We right rotate on P. Right rotate on P. After this, right rotate P. Same as 1. Very simple. Okay. Don't try to think about it. These are the only cases you can have. Then what other solution do you need? What other explanation do you need? Let's say parent, child, grandchild, T4, or I can say T1, T2, T3, T4. It is one single line, so I will just simply rotate. It is right case, so I will rotate it on the left hand side. Right case, move it on the left hand side. Left rotate on P. P will go, C will come above, P will go here, T1 will go over here, T2 will go over here. Okay, because it has to be greater than P, that is fine. G will be here, T4 will be here, T3 will be here. That's it. Balanced. Now you'll be like, Kunal, how do you know that the individual trees T1, T2, T3, T4 are balanced? Because we are starting from bottom up. Okay, that's why. Right case done. One more case left. Right left case. This is again very simple. Let's say I have my parent over here, my child over here, and my grandchild over here. Tree 1, tree 2, T3, T4. So I have to make it in one single line. I will start from the bottom up. So this one I will see C, and I'm going to right rotate it, right rotate on C. This will become G, and C will come over here, T4, T2, T1, T3. Now this is same as point number 3, right? Same as point number 3. So I will do left rotate on P. These are the only 4 cases. Why do we have these 2 extra cases? Because sometimes you get right left, sometimes you get left right. Those are the only 2 possible explanations. So you first make in a single line and then rotate it. And how do you know that individual trees are balanced? Because we're starting from the bottom up. That's the AVL algorithm. Insert it normally, start from the bottom node and find the node that makes it unbalanced from bottom up, then do the one of the 4 rotations. That's it. Very simple. Because that node made it unbalanced, right? That is why we're going to figure out the first tree that makes it unbalanced, and we're going to solve that tree. So when the subtree itself is not unbalanced, the other tree, oh yeah, that's one more other point. If the subtree itself, so we added one node, then we made sure that the first tree that it unbalances, we solve that. So this subtree we solved. So when the subtree is balanced, the above tree is also going to be fine balanced. If it is already balanced, try to understand, while we are adding elements, we are making sure tree is balanced. So before I add an element, let's say 100 elements are in the AVL tree. We know that those 100 elements, by definition of AVL tree, this is a very important point, I forgot about mentioning this. It's the intuition, the thing that will click. When you are trying to add, let's say you add 100 elements. Okay, I know that 100 elements are added, 100 nodes are added in the tree. I know it's an AVL tree, so I know it is a balanced tree. Because at every point of time, it will make it balanced. Now I add one more node and I'm like, okay, this node made a subtree, a part of this tree. For example, in this case, this blue one, this part, it made it unbalanced. So it will be like, okay, I added this one node, it made this tree unbalanced. So I will just solve this subtree. I will make this subtree balanced. And when this subtree is balanced, it is going to be fine because it's not going to affect the entire tree. Because the entire tree is already balanced. Make sense? Sounds good? Okay. So entire tree is already balanced, that is established. Only solve the subtree that became unbalanced. And if using that subtree other trees were unbalanced, those will also be balanced. Because the subtree was unbalanced, so it got balanced. Hence all the other subtrees that were, all the trees above it that were unbalanced because of it, those are now also automatically solved. Okay. Sounds good? We can take an example and see into a picture. Okay, so I got this example online from Geeks for Geeks, and I didn't want to make it all dirty, so this is looking much prettier. So here you can see they have a tree over here, and the node values, it says -1, +1, 0, 0. These are just differences in height, so don't worry about that. Okay, we'll see it in the code when we do left heavy and right heavy, like how to calculate it using a formula. So when you see, okay, Kunal, in these 4 cases, how are we going to write that in code? We'll see that in just a minute, don't worry. So here you can see that this is the normal tree, okay, it is balanced. It's saying insert the value 14, okay, it inserted normally 14 in the left hand 15, as you can see over here. It inserted 14 over here, no problem. Did this make it unbalanced? No, it didn't. Okay, move forward. Now here it says insert 3. So 3 is inserted over here, no problem. 3 is inserted over here, but this 3 made it unbalanced. Which subtree did it make unbalanced? 4, did it make 4 unbalanced? No. Did it make 5 unbalanced? No. Did it make 10 unbalanced? Yes. This is actually the same case that we had previously. So it's going to be like, okay, this is parent, child, grandchild. Parent, child, grandchild, tree 1, tree 2, tree 3. What is this case? Parent, child, grandchild, T1, T2, T3, T4. Right rotate. Right rotate. 10. Done. Fixed. I hope now it's clear. Now insert 45 in this example. It will insert normally 45 over here, no problem. Now this is making it what unbalanced? Is 40 unbalanced? No. Is 35 unbalanced? 1 minus 0 plus 1, no. Is 30 unbalanced? Yes, 30 is unbalanced. So P, child, grandchild. This is right case. So right case means left rotate. Right case, left rotate. How simple is that? How simple? Cool. Now here it's saying insert node 7. 7 will go over here, no problem. So 7 is making which balance, which subtree unbalanced? 6, no. 5, no. 10, is it making 10 unbalanced? Yes, it is making 10 unbalanced because this height is 2, this height is 0. So minus 2. So it is making it unbalanced. 0 minus 2. This is 0, this is 2. See, 1, 2 and 0. You know how it is 0, right? Height for every subtree. So height for this is, because this is only one node 0, height for this 5 is what? 1, 2. So 2 minus or 0 minus 2, if you're doing right minus left, minus 2. So 10 is unbalanced. So if 10 is unbalanced, then this is P, this is child, and is this going to be grandchild or this going to be grandchild? Grandchild is in the line of the number that is already added right now. 7 was added. So in the path of 7 to P, the one below child will be grandchild. This will be grandchild. So this is left-right case. Left-right case. Left-right case. Left-right case. First left rotate child, then right rotate P. Left rotate child, right rotate P. So left rotate on 5, left rotate on 5, then right rotate on 10, right rotate on 10. Not a problem at all. Very simple. Okay. Similarly, now this case, insert 15. 15 is added over here. Okay. Is it making 16 unbalanced? No. 9 unbalanced? No. No, actually wait. Is it making 9 unbalanced? Yes, it is making 9 unbalanced. Because left height is 0, right height is, no, left height is no, nothing. And then the right height is here 1. So it is actually 2. Yeah, 9 is unbalanced. So P, child, grandchild. So this is right left case. So in right left case, right rotate C, left rotate P. Right rotate on 6, 16. Yep. Then left rotate on 9. Yeah, tree is balanced. Cool. Using these examples, I hope you understand that when you find a tree that is unbalanced, which is like this, if you automatically solve this, then whole tree is solved, because originally whole tree was balanced. As original whole tree is balanced. This is the intuition behind it. This is where people get doubt, so I believe I cleared that doubt. Okay, sounds good. All right, now let's code this. It's very simple. Okay, so before we move on to the code, let me talk about the important part, time complexity. Time complexity. Let's say we talk about for adding, because that's a performance function we're performing. So time complexity, because at all the times tree will be balanced, so it will be log of n. Okay, log of n. Can you tell me the amount of time, the time complexity that the rotation is taking? Rotation is only at max 2 steps, either left rotate, right rotate, or something like that. So rotation is taking constant time, because I'm only rotating the subtree that was affected, and since that affected will be fixed, then all the trees will be fixed automatically, as I already told you, because the original tree was balanced, and the rotation at max, we're just doing 2 rotations at max. That's what we're doing, right? In left right case or right left case, we are doing 2 rotations. In left left right right, we are doing only 1 rotation. To maximum 2 rotations, which is constant. So total complexity comes out to be O of log n. Okay, now we can code. All right, let's start with the coding part. You can check out the link to my code sample in the description below. That is going to be nice, because then you can directly run the file on your browser. So I'm going to write tree to AVL, create REPL. And what I'm going to do is, I'm actually going to copy paste in my data structure algorithms. In the last one, we did trees. So I'm just going to copy paste the binary search tree, because we can use some of the functions, Binary search tree, create avl.java, copy paste it. AVL, AVL, hide it for now. And let me just double check, because whenever you copy paste, things can go a little wrong. So public class node, everything looks fine, node root fine. Insert, we will have to change a little bit, so don't worry about that. Populate with sorted is fine. Populate with sorted is okay. Display is okay. Is empty okay. Height okay. Balanced is also okay. Good. So if you don't know what these functions are, I mean, you obviously will, because we just did the tutorial. But this entire code I have not just copy pasted. We wrote every single line of this code in the previous lecture. So please watch the previous lecture. It doesn't make sense I write the same thing again and again in every lecture. So every single line I have explained in the previous lecture. Okay, now what do we need to do? So we are inserting normally, that is fine. But one thing we are changing is that we have to rotate for this node that we have just entered. So this node that we have just entered, let's say for root, and it's going to, in the end, when it goes down, 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 you know how the insertion works, right? So it's going down, 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 and in the previous example, like it'll go down, it'll go down, it'll go down, and then it will update it over here. So when it updates it over here, I have to call this node in, let's say I have to do what? I have to do rotate. So whatever you have just added, I will call a rotate on this node, and this rotate is actually going to return the node itself, which is the root. So we'll go up and up and up and up. So after rotating, so after it is done rotating, it will go up and up and up, and it will rotate the root. Return the root. Okay. So that's the one thing we have to change over here. And now what I have to do is I have to create a rotate function. Okay. So let's see how we can do that. I'm going to turn off the AI feature. Okay, I hope the screen is visible. The code can be found in the description below. You can directly click on run and you can run the code that I'm writing. So that's pretty cool. The link for this can be found in the description, just like every other link. So private node rotate node. Okay, we have to rotate. So no problem. Here, think about what is happening. Kunal, why did you call rotate over here? So when you're adding your node, in the end, it's going to be like, okay, node is equal to a new node added, then return. So it's going to rotate that node. It's going to rotate this node, and whenever you're trying to rotate, and then it's going to, it keeps on returning it like rotate on the nodes that I have called here in the previous part. Okay. So even though it keeps on calling it, it will not execute because these will all be balanced. There only will be one node that is unbalanced. So how do we make that check? I hope this is clear. You can run it on pen and paper. You know recursion very good now. So I hope this is clear. Please don't be confused on, Kunal, why are you returning this node? I am in the end returning in the end it will return the root node only. Okay. For every function call, first function call, it is going to return the node and it will pass it to rotate. Rotate itself is returning the node only. So in reality, it is just fixing the structure of the tree and then rotating the node itself. That is it. So private node rotate. So 4 cases. So one thing I want you to know is that in this case, when the height of, if you are on parent, if you are on this node, if the height of left minus the height of right is greater than 1, it basically means that it is left heavy, because left has more height, very simple. So you will just do right rotate. So left heavy is 2 cases, which is left and left right case. So in left right case, you can see, let me just write it down first. So if height of node dot left minus height of node dot right is greater than 1, then I know that it is left heavy. And now left heavy has 2 cases. So if I take this child over here, if the height of node dot left, p dot left, if the height of this tree and this tree is positive, it means that it is left case, because this is greater, so left case. So left case is this height will be more, this height will be less, that is left case, as you can see on the screen. So if height of node dot left and node dot left dot right. See, the thing is, don't try to think how these things are happening when it is right in front of your eyes. This is why in linked list many people get confused. In linked list you get questions like, okay, every 3 items you have to reverse or whatever. So when you're debugging it and writing it down, and it is, the diagram is telling you where all the arrows will go, then why do you need to think? There are 2 types of problem. One type of problem is in which you have to think. Other type of problems like this are the visual problems. The diagram is telling me what to do. There is no intuition behind it. Okay, whatever the diagram is saying, I'm doing. So if height of node dot left is minus height of node dot left dot right is actually positive, in that case I know it is left left case. What is the answer in left left case? Right rotate on P. P is node. So right rotate I'll create later on node. Similarly, if this is negative, meaning this height is greater, this height is smaller, means it is left right case. And left right case we do what? Left rotate on child means node dot left. So we do left rotate on node dot left. Node dot left is going to be equal to left rotate node dot left and then return right rotate on the original node. Right rotate on the original node. No problem. No problem at all. It will actually be equal to if this is negative. Make sense? Very simple. In recursion you will understand. In recursion I told you if the return type is node, then you're going to be returning node. So if you're trying to fix it for this node, if you're trying to fix it, then this function is actually should also return the type node, because this function is accepting node. That is why it's returning node. Otherwise it will give you error. It will not even let you compile or whatever. So if you debug it, you can debug it on pen and paper. I showed you the entire thing. When I add it in over here, it's going to say like, okay, new node added, return node. So it's going to call the node for this one. Call the rotate for this one. For this one it will not execute because none of the conditions will satisfy. Hence it will come out of here, and when it will come out of here, it will be like, okay, either over here or over here. So if it comes out over here, then load dot left will be equal to whatever it was. So node dot left will be equal to whatever it was, unchanged. And then it will be, okay, I'm not going to call rotate for this. Call rotate for this. It's going to say, okay, this does not satisfy the condition, so no worries. I will just return the node normally itself. Return the node normally itself. And this will either be returned from here or here. So it will be like node dot right, node dot left means C dot left. So for this node in recursion, node dot left will be equal to this only. So remaining unchanged, as you can see, remaining unchanged. I told you I won't show you the pen and paper stuff, but I'm still doing, okay. So now this for P, it will be like, okay, rotate it. So it's going to be like, okay, is this unbalanced? It's going to be, yeah. Then it will rotate it normally, and then whatever the node is supposed to be over here, which is going to be child, it is going to return that. And where it will return? From where it was called. So return the child that we have over here, and it will be called from here, so it will return over here. So this node dot left will now be equal to child, and this tree will be rotated. Okay, cool. Use the pen and paper, you will understand. This is very simple stuff, because we have done such questions before, and I showed you the problem by running it also. Copy paste. Now right heavy. Right heavy is when this is actually less than -1, and right case will be what? Node dot right case. Let's check the right case. Right case, okay. Node dot right dot left and node dot right, the difference between this and this should be negative, because this is small, this is big. So left minus right should be negative. So node dot right dot left, node dot right should be negative. That will be right case. And in right case, I do left rotate on the node. Left rotate on the node. Similarly, node dot right dot left, node dot right should be positive. should be positive. In this case, I'm going to say right rotate on child. Child is node dot right. So right rotate, that is going to be right rotate node dot right, and then left rotate on the node. In the end, just return the node. So even though this is being called for every single path as we move above, it will only run once because this condition will only be satisfied once. In other cases, just return the node itself. So in reality, this function that you're saying, Kunal, you were returning node previously and now you're returning it in a function. I'm still returning the node only, but I'm performing some functions. In one of the cases where the tree is unbalanced, it will adjust the size, adjust the structure, return the correct node. For everything else, it will return the node only. Not doing nothing, just returning the node only. What we were doing previously. Okay, now we have to create left rotate and right rotate. Okay, left rotate and right rotate. Let's see how we can do that. Okay, now right rotate and left rotate. Very simple stuff. So we have already done the overwhelming complex part. All the test cases, I showed you the run through of the code as well. You can also debug yourself. I've showed you how to put debug pointer into it, but I showed you like what the return node is, what the calling the function in the node return is. In the reality, it's only returning the node itself like previously in the previous binary search tree lecture, how it was returning the node in insert over here. But now it's only going to rotate it in one single case. And this if condition will only be valid for one single case because it will have that one case that will be subtree that is rotated, unbalanced. And we're doing right rotate, left rotate now. So we already have this thing over here. So ideally, think about when we were doing linked list. The diagram was telling us what to do and we were just coding that. I will do the same thing. I am shutting off my brain now because my brain, it's not required now, because whatever the diagram is telling me, I will code it. I don't even need to understand anything because it's not worth it. Because we've already understood how right rotate works, how left rotate works. Now the diagram is telling me what to do, so I will just do it. Understanding part is done. Okay, we did that in theory. So think about what all things we don't need to touch. T3 is not going to be changed. Don't touch T3. T1 is not going to be changed. Don't touch T1. T2 will be changed. So P, just gonna write it down. Right rotate across node P. Node child is equal to P dot left. Node C is equal to P dot left, no problem. Node T is equal to P dot left dot right. Now, or C dot right. T is equal to C dot right. T is equal to C dot right. Okay, now right rotate. C dot left will become P. And C dot right will become P. C dot right will become P and P dot left will become T. Done. That's it. One last thing you have to do is update the heights now, because C was added above, P was coming down, so update the height. P dot height is equal to math dot max Cool. So new height is going to be equal to maximum of left and right plus 1 for this. We have done the height formula before, so don't worry about that. Similarly, C dot height will be equal to math dot max C dot left C dot right plus 1. Now what is the new node? New node is C. Return C. I am telling it again and again. The only intuition problem that you are going to have, I know you are having this doubt, is over in this line 43. Please try to understand that in original format it was return node. Right now also it is return node only. See, it is doing nothing but return node. But for that one case in which the subtree is unbalanced, it will balance in, then return the node. So new node will be returned like C, and that will be added over here. So it will return, then where it will be returned from where it was called, which is somewhere over here. And then that new child will be equal to the node dot left of the above that one, as I showed you in the example right now when I was writing this code. Okay, it was very simple. It is, don't overthink it, it's very simple. I shared it like 3-4 times. I won't share it again now because then it will get cringy. Anyway, so I told you where you might get doubt. I solved that doubt. Now we can move forward. Okay, now left rotate. Left rotate is very simple, copy paste. You can just do the, use the, this thing over here. Okay, so again, no need to think. I will take in this example only. It's saying C. So I will have node C over here. Left rotate. So node P is going to be equal to C dot right. Node P is going to be equal to C dot right, and what will remain unchanged? T3 will remain unchanged. T1 will remain unchanged. T2 will be changed. So C dot right or P dot left. Okay. So here we have P dot left is equal to my T, and now how to change it? So if I'm changing it left rotate, then P dot left becomes C. No problem at all. And C dot right becomes T. No problem. Similarly, P dot height and C dot height. Looks good. Now new node is equal to P, so I will return P. That's it, AVL tree done. Very cool stuff. Simple, right? Now you can run this. Let's try running it. Okay, so here in the main function I can write my code. I can say AVL tree is equal to new AVL tree, and let's say I'm trying to insert, ascending order. So in binary search tree it will just make a line like I showed in the previous one. Int I is equal to 0, I is less than, let's say, 1000, and I plus plus. I'm going to say tree dot insert I. If I check the height of this in a binary search tree which is not balancing, it will be like, okay, right, it will give 1000. So system.out.println tree dot height, this should give log of 1000. Let's see. Okay, so log of around 1000, so it should give me 1 plus log 1000. So log 1002 plus 1 3. I inserted 1000 elements in a tree. In binary search tree, height would be 1 1 1 1. Just go right, as I showed in the previous example. This example. But now no, it's balancing it. That is why always height will be log of n. Simple, very easy, very nice. Self-balancing binary tree is a piece of cake. Done? Okay, so lastly, I'd say you can take a screenshot, share it on social media, #DSA with Kunal, join the Learning Public Initiative. I'll make tutorials much faster, at least 4 videos you can expect in a month. And as the next one's recorded as well, I have to edit those. But I wanted to make sure we do this one first before jumping on to the questions, because these are some of the concepts that are being used. So few things. Number 1, like. Number 2, comment. Number 3, take a screenshot and share with #DSA with Kunal. And that's it. These 3 things you need to do. For follow-ups, the assignments and everything, notes, and the code link can be found in the description below. So you can directly use the URL that I will share with you in the description below, and you can just run it after signing up. You can run it and you can run the code that I'm writing, make it, modify it, fork it, do whatever you want. And it's very nice because you can do it right from your browser itself like I'm doing. So for teaching, it makes it much more convenient. So yeah, like, comment. If you comment, more people will view it and more views will get, and more people will learn from these free courses, and more motivation I'll get to make such videos. So like and comment is at least something you can do. And share, you can do it. If you don't want to, that's fine, but like and comment, please do it. If you've watched it till now, please like and comment. I cannot stress this enough. And assignments, everything, all the links, code, description below. And I'll see you in the next one. Have a great day. Bye. If you have any doubts, comment section. Yeah, bye.